Was the dimension of our A is rank of A. In the previous example, for instance, we had A to be 1, 2, 3, 4, 4 by 5, right? And the rank was 3. So it was the rank efficiency situation. So if somehow you had an m by n and you get the rank of A greater than the minimum of m and n, it means that you have made a mistake somewhere. Now for system of equation which is A m by n multiplied by x n by 1 is equal to b of m by 1 if rank of A is not equal to rank of this new matrix which is adding, concatenating B to the last to the end of our matrix A, then means that B does not belong to RA. So we had it before. So what can we understand? So A is a linear transformation, isn't it? Right? So what happens is whatever you give to A, A will take us to RA, isn't it? I mean, we had this. And the A was taking us to the RA. Right? It cannot take us anywhere else. Now, if we have X, the X belongs to V1. So any X belonging to V1, with the A we go to RA. If B is not in RA, it means that B is here. A multiplied by X means that X is being moved by A into RA. But B is not into RA. And we say that AX should become B. So what do we conclude? Change your sentence. The transformation is fixed. What is not possible? The equation so if equation is not possible, it means equation. Okay, let's put it this way. This is a set of equation, right? And what we do, we solve it and we find that x1 is 1, x2 is 0, x3 is something. But what happens is this. The aeroplane will take you from any place that you are right now to, let's say, Berlin. Okay? Take you to Berlin. And your parents wants to visit you. So, and your parents are in Frankfurt, which is not in Berlin. So, if you get into the aeroplane and you go to the Berlin, can you meet your parents? No, because your parents are not in Berlin. Why? Because the aeroplane can only take you to Berlin. So the aeroplane is A, and we are X, and we want to go to our parents, which is Frankfurt, but we know that the aeroplane takes us to the Berlin. So it means that the equation, can the equation lead us to Frankfurt? No. No. So the equation has no answer. Has no solution. Why? Because it only takes us to RA, but B is not in RA. And we want X goes to B, but A does not go to B. So it means that there is no solution. There is no solution. We had this one, I think, at the beginning of the first weeks of the class also. No, I want you to like visualize it so you understand that why the equation has no solution. Because A can only takes us within this territory, and we want to solve something which is out of this territory, and A cannot by any means takes us to that territory. So we understand that if B belongs to RA, then we have a solution, right? So in order for B to belong to RA, it means that this rank should be equal to this rank. Now, one question, another clever question. And the question is that, what is the meaning of this statement? Rank A is equal to rank AB. Or what is the meaning of rank A is not equal to rank A and B?
The rank of A should be less than, well, it's actually going to be less because if you add concatenate with B, so it means it's less than the independent columns.
You are saying something which can be true, but irrelevant to my question. My question is this. What does it mean rank A, let's say, is equal to rank AB? Or what does it mean that rank A is not equal to rank AB? Because if we understand it, then we understand this, then we understand this. In order to answer this one, forget about your notes, it's not in your notes. So let's do it like this. AX is equal to B has a solution. Okay? AX is equal to B has a solution. Do you know what is B? I mean, X is a vector, isn't it? So, what happens when we are multiplying this one with a vector it means that we are starting to linearly combine the columns or the rows of this matrix to come to a column vector, right?
Yeah.
So we are, I'm repeating myself, we are linearly adding all these rows in order to come to one number, and we are getting our B. What are the coefficients of this combination? Is in X. So, what can you tell me about the column vector B and the columns of A? How did we achieve this? By kind of linearly combining them, right? What are the coefficients of this linear combination? x1, x2, x3 till xn, right? So what can we say about this column and the columns of this?
They probably have to be independent.
No, we don't talk about the independence in A. I'm saying that what can we say about B and the all columns of A? I mean, how do we get B1?
B11.
It will be A1 by n multiplied by xn by 1, isn't it? So it means that A1, 1, A1, 2, A1, 3, A1, n, these all will be multiplied by x1, x2, x3. So in other words, I am linearly combining them to get the B1. Then I will linearly combine the next one in order to get the B2. So I linearly combine the last one in order to get the last one. So if I look at the whole, what can I say about B and the columns of A? B has been produced by linearly combining all those columns, isn't it? Because A's are fixed and X are the coefficients. So what we are doing, we are using these coefficients, we are just combining all of them and we get B. And then it means that we have a solution, right? We have a solution. If we have a solution, if this is true, it means that actually we are combining all these columns in order to get B, right? So this means that if I am putting B next to A, I am not introducing anything independent. It's a dependent thing. And if I'm adding one dependent column, do I change the row? Do I change the rank?
No.
No, because rank tells me that number of independent ones. So if I add the dependent ones, I know that rank is not being changed. So it means that if this rank A is equal to rank AB, means that B is linearly depending on A. Which means that if B is linearly depending on the columns of A, it means that this has a solution. So whereas if rank A and rank A and B are not equal to each other, it means that adding B is linearly independent from what we have in A, because we are introducing a new rank, a new value, which means that this term cannot be true, because if it wants to be true, B must be linearly a combination of columns of A. So what does it mean that rank A is equal to rank BA? It means that B is a linear combination of rows of A. When they are not equal, it means that B is independent from A. So if B is linearly depending on all A's, it means that because it means that X exists, that we have combined somehow these ones in order to get B, which means that we have a solution. If it doesn't exist, it means B is linearly independent. If this is not equal, it means B is linearly independent, which means that there is no way that you can combine these A's and get B. Now, did you see the image? So, if rank A is not equal to rank AB, means B is not in RA, which means the equation has no solution. What will happen if rank A is equal to rank AB? In other words, if B belongs to RA. If do I need to wait?
No.
So if rank A is equal to rank AB, then B belongs to RA. So now B is a member of RA, so it means that there is a way that we can assign sets of x. We can find an x which we will assign it to B. So the system, the equation has an answer. Has an answer. But now there is two things when we say that we have an answer. One thing is that we have one unique answer, which means that B belongs to RA, and there is this unique x which goes to B, or we have infinity many answers. It means that there exists lots of other xi's which they also goes to B. So the question is that when do we have one unique answer? When do we have infinity many answers? Again, this was something that we had it before. We discussed that one. If null space of A is empty, is 0, we have the unique answer. If it is not, then we have infinity many answers. We remember from the undergraduate algebra or calculus, when do we have infinity many solution in a system of equation? When the number of equation is less than the number of unknowns. Right? When don't we have a solution if the number of equation is more than the number of unknowns and they are independent? When do we have a unique solution? When the number of equation is the same as the number of unknowns that we have. Right? 3 equations, 3 unknowns, it was always what we used to solve. For this one, we usually solve it in a parametric form. So we said that a range of space, a range of A is. We said that the range of A, which we call it RA, is the set of W's belonging to the W vector space, where W is equal to AV for V belonging to our domain, right? So if you want to show it in a picture form, this is V, this is W, and this is A. In some books, they say that the range of A is also known as image of A, and they show it by the IM of A, but we stick mainly with RA. And the null space of A, which we showed it with the NA, is the set of V's belonging to V in the form that AV is equal to 0. AV is equal to 0. Can you tell me that? Okay, it's easy to see that V is here. V is here. V belongs into here. So where is null space? Null space is going to the 0. This 0 is a member of W. Is a member of W. But the reason I wrote it was because in some books we have different name for null space. And NA is also known as kernel of A, and they show it as a ker of A. So if you are using some books and you see that they use the word im A and ker A, you understand that they are the range space and null space that we had before. Theorem. Let A be this linear transformation from V to W. Be a linear transformation. Then we have RA and NA each be a subset of, subspace of
W.
This one is subspace of W. What about the other one?
Also.
Now, look. For the RA, we are defining sets of vectors in W.
Mm-hmm.
In null space, we are defining sets of vector in V. So this is a subspace of V. So in general, RA and NA are subspaces subspace of different vector spaces. Well, I've used in general because you can come with lots of examples that your V and W are the same. Do you have any question? Okay, finish writing. Any question, Dana? Right? If you have no question, we'll stop here. You can stop the video.